always, the key is for you to understand stuff, not just be able to like solve some problems or plug some numbers in. And there's some pretty tricky stuff here. So what I want to start with is just a quick reminder of what we've done so far with angular motion. And what we did is we said, okay, if we think about things that are rotating or spinning, moving along a curved path, we can think about how far they go in terms of rotations or some sort of angular measurement like degrees or radians. We can think about how fast they're moving in the same way. We can think about something that makes a quarter turn in a second or that rotates at 1 radian every 2 seconds or 3 seconds. We can think about degrees per minute. And we can also think about acceleration. We didn't talk about it a bunch, but the idea that as things rotate, they can potentially spin faster and faster and faster, or slower and slower and slower. They could even reverse direction. So we can have angular displacement that looks at rotation in degrees or radians or rotations. We can have angular velocity, and we can have angular acceleration. We also can think about how far something moves as it rotates. So the gigaw here, if it rotates a quarter turn, we don't know how far it goes because we don't know how close it is to the center of rotation. If it rotates a quarter turn and it's really close to the center of rotation, it doesn't move very far. This is just like a few centimeters. But if it's far from the center of rotation, it has to travel a long distance, linear along that curved path, in order to make that quarter turn rotation. So we figured out that if we know the distance to the center of rotation, we can move back and forth between the language of angular motion, radians and degrees and rotations, and the language of linear motion, which is along a curved path. We're not looking at things that are moving in a straight line, but we look at that curved path and we say, well, if we took that curved path, and this is a disaster. This is just not supposed to be happening like this. If we look at that curved path and say, well, this is the path it traveled, how long is that path? We straighten it out and we measure its distance in meters or centimeters. So we can take a curved path, turn it into a straight line, and that's what I've been calling the linear equivalent. And we can move back and forth. We can think about how something's rotation can be converted to a linear distance or velocity or acceleration if we know how far it is from the center of rotation, and vice versa. We had some equations that relate our angle in radians to the linear distance, the arc length, s, and the distance to center of rotation, theta equals s over r. We know that angular velocity is equal to the linear equivalent, the speed of the object along its path, divided by r. And we know that the acceleration of an object, how much it speeds up or slows down along that path, which I call the tangential acceleration because it's tangent to the curve, that acceleration will be equal, or divided by r, will tell us the angular acceleration in radians per second squared. And then we also looked at the idea that we can take all of our kinematic equations that we used under conditions of constant acceleration, and they all still work. We just have to use those weird new variables. We have to use theta for position, we have to use omega for velocity, we have to use alpha for acceleration, but then our same 3 kinematic equations will apply and allow us to make predictions about displacement, velocity, acceleration, or time, as long as we have an object that is rotating, moving along a curved path at a constant rate of angular acceleration. And today we're going to look at what happens when we have angular acceleration. We're going to look at how we get there. And we're going to kind of split this into 2 parts. So today I'm going to look at the ingredients that go into causing angular acceleration, and we'll explore further how those get put together on Thursday. And so for today, the goal is going to be for you to explain 2 really difficult concepts. One is called torque, one is called moment of inertia. The equations are easy, but using them is really hard, and understanding what they are and how they work is going to take some thought. You're going to have to really process. And then on Thursday, we'll take all that information and we'll plug it in to a version of Newton's second law that is based on our angular measurements and quantities rather than linear measurements and quantities. So the quick review, you don't need to write this down because this is all stuff we've done already. Back in the day, we realized that what causes acceleration in an object is an overall force. If you have an overall force, objects will accelerate. And we figured out that Newton's second law basically relates acceleration proportionally to the overall force applied and inversely proportionally to the mass of the object, which means that if we have an object and we apply a larger overall force to it, we should get more acceleration. And it doesn't matter where that force is applied. When we think about an object that is moving in a straight line, we sort of imagine that it is just located like in a really, really small, infinitesimally small dot that is located at that object's center of mass. And it turns out that by and large, that is accurate. We can very accurately model most objects in most conditions as infinitesimally small points of mass that are experiencing forces. That's not universally true, but it's true for anything that we're ever going to do in this class. If you were to lift me up to the ceiling and drop me onto a soft mattress or something, then I would accelerate down at a constant rate of about 9.8 meters per second squared, as if I were compressed into a really, 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 really tiny ball of mass that was equal to the mass of my body right now, and my clothes and my wallet and everything else. But actually, that's not entirely true. And the reason is because the Earth's gravitational field is such that the further away you get from the center of the planet, the weaker the force is. Which means, technically, if you were to lift me up to the ceiling and drop me, if I were upright, there would be a larger force acting on every kilogram of mass at the top of my body, a smaller force acting on every kilogram of mass at the top of my body than there would be on every kilogram of mass at the bottom of my body. My head, every kilogram of my head would weigh less than every kilogram of my feet. And we wouldn't notice a difference, we wouldn't be able to measure it, but in certain extreme circumstances we can. So for example, black holes have such a strong gravitational force that they can tear things apart because the force acting on one part of an object might be significantly different from the force acting on another part of an object. And we actually see stuff like that right at the event horizon of a black hole, where we get particles that spontaneously come into being. They're right next to each other. One of them gets sucked into the black hole, the other escapes the black hole because the force is slightly different in the two locations where they are. So there's all sorts of stuff that quantum physicists and particle physicists have to think about that involve things that really do take up space, and the amount of space they take up is significant. But for our purposes, we just think of everything as being the exact same size. And if we think about how mass affects acceleration, it has the opposite effect. Larger mass will result in less acceleration for any given force. So if we double the mass of an object and pull on it with the same force that we pulled on the original object, we'll get half the resulting acceleration. And the location of that mass, how the mass is distributed in the object, doesn't matter. We're imagining that it's all compressed into one teeny tiny point. And so it all behaves the same. It doesn't matter if the mass is spread out or together. So if you were to put me on a wagon and pull the wagon, I could put my arms and legs out, or I could pull them in, and it wouldn't make any difference to the force that you would need to apply to get me to accelerate at a certain rate. And again, it's not entirely true, but it's so close to being true that we act as if it is true. With rotation, it's really different. With rotation, it turns out the location of force matters and the distribution of mass matters. So when we think about rotational dynamics, angular dynamics, we can't just think in terms of forces and mass. We have to think about forces and where they're applied, and mass and how it's distributed. So when we talk about acceleration, we are, for now, are going to be talking about the acceleration that we think of when we look at an object that's rotating and we think of how quickly it's spinning around. And we can think about that in two ways. One, angular acceleration. This is looking at how quickly this object is speeding up or slowing down in terms of rotations per some unit of time, or degrees or radians per some unit of time. So if I spin at about 1 rotation per second, 1, 2, 3, 4, I could slow down, and now I have, that would be we might think of it, since I'm spinning in the counterclockwise direction, we might think of that as a negative angular acceleration. Or we can think about it in terms of tangential acceleration. That's the quantity we were thinking of the other day. And that is just looking at instantaneous linear speed along this curved path and how that's changing. And we can move back and forth between these two because alpha, which is angular acceleration, is equal to tangential acceleration divided by r, which is the distance to the center of rotation. These two things effectively describe the same kind of change in motion. If something has tangential acceleration, it will also have angular acceleration, and vice versa. There's two other kinds of acceleration we can think about, though, and we're not going to think about either of these right away. I just want to point them out to you. One is we can think about centripetal acceleration. Centripetal acceleration, centripetal means toward the center. And that's the acceleration that causes this object to change direction in a fixed xy coordinate space. So if you look at an object like the Giga that's spinning around in a circle, even if it's traveling at a constant speed, it's never moving in the same direction. Every instant it's traveling in a different direction relative to a fixed xy coordinate space. We can't get acceleration, which change in direction is, without an overall force. So that means two things. One is there must be an acceleration acting on this object. The other is there must be an overall force on this object. And in this case, both of those quantities are directed straight toward the center of rotation. The acceleration tells us how quickly the direction of this object is changing. It might be moving at a constant speed, but it's changing direction at this rate. The centripetal acceleration is equal to v squared over r. You don't need to know that right now. You will need to know it later. And I think this is also equal to omega squared times r, although I'm not sure about that. And I was going to look it up last period, and I asked the students to do it, and I forgot. And I think that's right, but I'm not 100%.
It's right.
That's right, okay. It's the same, and this is just because omega is v over r. So it ends up being the exact same thing when you do all the math and you multiply it. So so what that means is that that when we have centripetal acceleration, we're going to have an inwardly directed force as well. So we're not going to worry about this until we start talking about orbital motion, because that's when it gets interesting. In this case, the centripetal acceleration is provided by force in the string itself, tension. There's tension in the string. I can feel it. In the case of orbital motion, that force is provided by gravity. And so we can come up with all sorts of really cool relations that involve gravitational force, that involve centripetal acceleration for objects that are moving in orbit. And then, since centripetal acceleration is toward the center of the circle, tangential acceleration is instantaneously tangent to the circular path, we could combine those two quantities to come up with an overall linear acceleration, and it would look something like this. The tangential acceleration would be in one direction, the centripetal acceleration would be at a 90-degree angle to that, and the overall net acceleration would be offset from both of them. Something that is traveling at a relatively low speed, but accelerating quickly tangentially, would have a large tangential, very small centripetal acceleration. Most of the acceleration would be in the direction of its motion. Objects that are traveling at a high rate of speed and have a relatively small tangential acceleration, most of the acceleration is centripetal. On the Ladybug app that we used, you can see that. And what ends up happening is if you look at the overall linear acceleration for an object that starts from rest, it starts matching the tangential acceleration, and then over time, it comes closer and closer to the centripetal acceleration. The faster it goes, the more the overall acceleration and the centripetal acceleration are the same. We're not going to worry about either of these two things right now. The overall linear acceleration is only something that AP students are going to have to think about. You don't have to worry about this if you're not in AP Physics 1. Those of you in AP Physics 1 should be able to do this math and should be able to think about what I just explained about how overall acceleration is going to kind of change as something speeds up. Those of you in the regular class will deal with centripetal acceleration when we talk about gravitational motion. All right, so the big concepts that we need to think about today have to do with our distribution of mass and the location of forces that are acting on objects that are rotating. So when we have an object that's rotating, it's not enough to think about how much overall force is being applied to that object if we want to know its acceleration. We also need to think about where that force is applied. And you've seen that a couple of times. Ideally, you saw that when you were using our cheesy little PVC pipes, and when you were applying forces, what you should have seen is that if you pull or push on the PVC pipe close to the center of rotation, it doesn't accelerate as quickly as it does if you push with that same force farther away from the center of rotation. It's much easier to see that with objects that are more difficult to move. So like this door, if I push on the door with a reasonably small force, I can open it from the end, but if I push close to the center of rotation, I can't open it with that same force. When we rotate objects, it's not just the force that matters, but how much leverage we have as well. And leverage is just the distance from where that force is applied to the center of rotation. So there's an equation for this, and it looks like this. This little fellow is the Greek letter tau, it's a lowercase tau, and that is our variable for torque. Torque is angular force, and that's equal to R, which is the distance from the force to the center of rotation, also called the lever arm, times the actual force itself. So you can see the units are going to be newtons, the units of force, times meters, the units of distance. The farther away you are, the more torque you get for a given amount of force. That's leverage. And you know about leverage because you use it all the time. If you need to like move something heavy or tear something apart, you use a crowbar because it gives you more leverage. If you had a bolt or something that you needed to undo, like if I wanted to unscrew this sink top right here, if I use my fingers and I can't do it, then I might need to get a wrench. And with a wrench, then, okay, I still can't do it. But because of leverage, if this wrench doesn't work, I can get a bigger wrench. So I've got a bigger wrench, and I can use this one instead, and now I will be able to, okay, that one doesn't work either. But I can I have a bigger wrench, and that is going to definitely allow me to do this. And I can't quite get it. But lucky for you all,
Wrench.
I have the big wrench. The big wrench can take care of anything. If I want to, like, this is the size of wrench. Like, if you've ever seen one of those like lamp posts or street light things where you look down and it's got just a huge bolt on there, these are the wrenches that people use. Now, nowadays, people use power tools for all that stuff, but the reality is that nothing beats leverage. If you've got if you've ever had a flat tire on the freeway, you know that to get your tire off, you use that like really long tire iron because you need the leverage. Those bolts that attach your tires to the car they're not messing around. Those things aren't tightened on there by hand, because you don't want your wheel coming off while you're driving down the freeway. So you got to use a lot of torque to get those things taken apart. As you all know, I have lots of famous Breegar stories, and one of my favorite stories involves an application of torque, and this was a few years ago, so this was one of the most awful experiences of my life, and I know that that's not saying much because it's really not that awful of an experience, but I'm a big baby, and so it was an awful experience for me. It was winter break of 2021, and you might not remember, but winter break, the first few days of winter break 2021, it poured. It was sort of warm, and it poured, and there were several days where we got like 2 inches of rain, no exaggeration. Like every day I would look at the rainfall totals and it would be close to 2 inches. And so one morning I got up, and it had just been pouring and pouring and pouring, and I thought, you know what, I better look at the basement, because sometimes I get a little bit of water in my basement. Well, I went into the basement, and the stairs are here, and the water started here, and the basement floor was about 6 or 7 inches below that. Right, so I had a good half a foot of water in my basement, and my water heater was sitting here, and it was totally flooded. And there's the way the water heater works. There's a burner down here. Mine is natural gas. So luckily, there was no wires in the water. There could have been just a tremendous shock hazard if any of this stuff had been wired up. But I didn't have to worry about it because it's a natural, my water heater is natural gas. But I looked at that, and my first reaction was to just go back upstairs. I just went back to bed. That was like I couldn't deal with it. But then my second reaction is I went to Home Depot, and I got some pumps, and I was able to get the water level lowered by several inches, but it was still up above the burner in my water heater. So what I did was I got a bunch of like small pieces of wood, some 2x4s, and then I got some big like cement blocks, and then I went and I had just a big 2x4. I got the biggest 2x4 I could find, and I wedged it underneath the water heater like this, and then I applied all of my body weight to that to tilt the water heater a little bit, and then I kicked one of these wooden blocks under there, and then I went around to the other side and I did the same thing over there and kicked one of these blocks under there, so that raised it up like an inch, and then I did it again, only this time it was up higher, and so I was able to get the big cement blocks under there, and I got it, I was able to get it out of the water and like get my water heater working again. And you know, like I didn't need the water heater. I could have like, you know, like hot water is a luxury, it's not a necessity. But I'll tell you, this was big for me in terms of morale. Because I was pretty crushed when I walked down there and I saw that my basement was flooded and like thousands of dollars worth of damage and all that good stuff. This is what allowed me, this like success is what allowed me to feel like, okay, I can do this. And so then I did, I like fixed it. But yeah, there's more to this story. This is a super interesting story. The more to this story that I'll tell you is I'd hire a company to come in and replace my sewer line. And they didn't tell me that there were 2 drains that went into it. There was one drain that's higher up, and that's where like the shower and the bathrooms and the sinks and the washing machine all went. And then there was one drain that was way low down from my basement. That's what kept my basement from flooding. They saw that and they replaced it. They took out the old pipe and they looked at it and they were like, huh, there's 2 attachments here. I'm just gonna put one back. And so they hooked up luckily they hooked up the sewage part. So this was just rainwater in my basement, thank goodness. Otherwise I would have had to literally burn the entire town down. And, like we all would have had to move. But it was just rainwater, but still, like they didn't hook it back up. So there was like thousands of dollars worth of damage, and I sued them. I filed a lawsuit for the first time ever. I did win, and I got some money for them, and then they like went out of business. That's all right. I didn't ruin them. They sold out to somebody. I don't feel bad about it. They blew it. They really dropped the ball. Let this be a lesson to you. Always, if you end up being like an excavator or an electrician, anybody in the trades, like ask. If you find, like, if you're doing wiring in somebody's house and you're like, here's a wire, it's connected to this wire, it's connected to this third wire, don't be like, well, I'm just gonna connect these two up. I don't know where this one goes and therefore it can't possibly be that important, because that might be like the thing that like provides the furnace, the power to the furnace or whatever. Anyway, don't mess around with that stuff. None of that is of critical importance, but I like thinking about that stuff because this is where the real physics gets applied. Okay, and then, so when we think about changing the rotational speed of something, we do that by applying overall torque. Since torque is related to both force and leverage, we can increase angular acceleration by increasing either the overall force that we apply or making that overall force applied at a distance farther away from the center of rotation. So if I want to have this door swing open quickly, go from being motionless to moving rapidly, I could do it by applying a sort of medium-sized force at a reasonable distance, or I can apply a smaller force at a large distance. If I want to make it happen by pushing closer to the center of rotation, which sometimes you have to, then I have to apply a much greater force. I can still make the door open, but I can't do it by pushing gently anymore. So you increase torque by applying a larger overall force or applying forces farther away from the center of rotation. And we take advantage of all of that in engineering. A bicycle is a great example of a relatively complicated system where you're applying forces closer or farther from the center of rotation to maximize either distance or force. Leverage takes advantage of the fact that in general, people think it's easier to push things far than they do to apply a large force. It's a trade-off. Leverage is a trade-off. If I want to open that door quickly, I have to move my hand farther if I push farther from the center of rotation. Sometimes it's easier to like move a shorter distance, so sometimes we do that as well. This idea that angular force, torque, is force and the location of that force is mirrored in what we call moment of inertia. Moment of inertia is a weird name, but all it really means is angular mass. It's just mass. It's the same kind of mass that we were looking at before, with the difference that the location of that mass matters. So when you are moving something in a linear fashion, it doesn't matter where the mass is located. In this case, for this blue bar, there's a lot of mass here, there's a weight right here, and there's a weight right here. And I don't really notice where it is if I move it up and down like this. I don't really notice where it is if I move it left and right like this. But if I spin this, I can feel that weight is far away from my hand. I can feel it. It's like kind of hard to stop and it's kind of hard to start. That is angular mass that I'm feeling. And it's related to both the mass itself, the fact that these are weights, and the distance from the center of rotation. So moment of inertia is really tricky because it depends not just on how much mass there is, but where that mass is located relative to the center of rotation, which can change. I can rotate this bar like this, the center of rotation is right in the middle, or I can rotate it like this. Now the center of rotation is all the way on the end. I can rotate it like this. Now the center of rotation is on an axis longitudinally through the cylinder. I could rotate it anywhere. I could rotate it like this. And so in order to know an object's moment of inertia, we have to be able to determine how much mass it has and where all of that mass is located relative to the object's center of rotation. Sometimes we can do that with a relatively simple formula. And you can look it up. So if we have a sphere that's uniform, and we know its mass, and it's rotating right through the center, then we have a formula that we can use to calculate its moment of inertia. If we have a cylinder like this, and like the one that I was just using, and it's uniform, we rotate it about the center, then we have an equation we can use. We just need to know the dimensions. This hollow tube, if I wanted to know the moment of inertia of this hollow tube, I would find its mass and measure how long it is. And then I could plug it into one of these equations and figure it out. Super easy. Most things, though, are not uniform. And they're certainly not uniform about their center of rotation. So if I want to take this bottle of dishwashing soap and spin it around my finger like this, then the center of rotation is right here, and it's not uniform. The mass is like not evenly distributed. It's not a uniform shape. It's like got all sorts of curves and angles, and it doesn't show up in this list. I wouldn't even know what to measure here. Like I could measure its mass, but these all have like an L and an R, and I wouldn't know what to measure here. What's L? The distance from where to where? What's R? The distance from where to where? It's not obvious on this. So one of the things that we will find out is that for most real objects, the only way to actually determine the moment of inertia is to find it experimentally. So what we're going to be working with primarily are these concentric pulleys. So this is one right here, and they're old, but they work fairly well. And we can think about things like, hello, welcome back. We can think about things like, well, how much force is acting on these and where's that force located? And we might want to use that information to make predictions. But we also need to know, just listen for a sec, please. We also need to know about the angular mass. Angular mass affects how quickly rotation can change. Things that have more mass or mass that is farther from the center of rotation will tend to have less acceleration for any overall torque. Which means, for something like this, before we can make predictions, you need to find what its moment of inertia is. Okay? And we'll do a little bit of that on Thursday. Some of that experimental stuff will wait until next week instead. Those of you who just came back, all of this is being recorded. I'm going to post it. Bye.